Download this code from codegive.com, link in the description below. 53 Priority-based scheduler for Superloop architecture, a detailed tutorial. This tutorial will guide you through implementing a 53 priority-based scheduler within a Superloop architecture, suitable for embedded systems or environments where real-time determinism is crucial. We'll cover the concepts, data structures, code implementation, and considerations for optimization and robustness. What is a Superloop architecture? A Superloop, also known as a main loop, is a simple program structure where the code continuously iterates through a set of tasks. It's a fundamental building block for many embedded systems because of its predictability and low overhead. The basic structure looks like this. Why priority-based scheduling? While a simple Superloop executes tasks sequentially, it lacks the ability to prioritize tasks based on their importance or urgency. A priority-based scheduler addresses this limitation by allowing you to assign priorities to tasks and ensure that higher priority tasks are executed before lower priority ones. This is essential when dealing with time-critical operations or events. Why 53 priorities? The choice of 53 priorities is somewhat arbitrary and likely determined by specific application requirements. However, it provides a relatively fine-grained priority system, allowing for a good level of control over task execution order. Using a number like 53, not a power of 2, can sometimes force better usage of memory depending on how the data structure is implemented. Key concepts and data structures. 1 task ** a function that performs a specific operation. Each task will have an associated priority. 2 priority ** a numerical value representing the importance of a task. Lower numbers typically represent higher priority, example 0 is the highest, 52 is the lowest. 3 task control block, TCB, a data structure that holds information about a task. It will contain at least * a pointer to the task's function. * the task's priority. * a flag indicating whether the task is ready to run. * optional, task-specific data, example a counter, input parameters. 4 ready queue, or priority queue, a data structure that stores the tasks that are ready to be executed, organized by their priority. In our case, a common and efficient approach is to use a bit mask for each priority level, indicating if a task is ready to run at that level. Implementation steps. 1. Define data structures *. 2. Define the ready queue, priority queue. We'll use an array of bit masks. Each element in the array will represent a range of priorities, and each bit in the element will represent whether a task is ready at that priority level. This is a space-efficient way to represent the ready tasks. 3. Task registration function *. This function adds a new task to the system and assigns it a priority. 4 ready/unready task functions *. These functions set or clear the ready flag in the TCB and update the ready queue. 5. Scheduler function *. This is the heart of the scheduler. It determines which task, if any, should be executed in the current iteration of the Superloop. It iterates through the priorities, looking for the highest priority ready task. 6. Example tasks. 7. Main loop *. The main loop initializes the system, registers the tasks, and then continuously calls the scheduler. Complete example code, with explanations. Explanation of the code *. Headers *stint.h provides standard integer types, stbul.h provides boolean type, and stdio.h is used for printing in the example tasks, remove for bare metal embedded environments. *task_function_t*, a type definition for task functions, Functions that take no arguments and return void. *TCB underscore T asterisk the task control block structure, holding information about each task. *tasks asterisk a global array of TCBs. This is where all the tasks are stored. *number underscore tasks asterisk keeps track of the number of registered tasks. *number underscore priority underscore levels asterisk defines the number of priority levels, 53 in this case. Ready queue asterisk the core data structure for the priority-based scheduler. It is an array of bit masks. Register underscore task, registers a new task with the scheduler, adding it to the tasks array and initializing its TCB. Set underscore task underscore ready, sets a task as ready to run by setting its ready flag to true in the TCB and updating the corresponding bit in the ready queue. Set underscore task underscore unready, sets a task as not ready to run, clearing the ready flag and the corresponding bit in the ready queue. Scheduler, the scheduler function finds the highest priority ready task by checking the ready queue and executes it. It iterates through the bit masks, finding the first set bit, which indicates the highest priority ready task. Task 1, Task 2, Task 3, example task functions. Replace these with your actual task code. Idle underscore task, an optional idle task that can be executed when no other tasks are ready. This can be used to put the CPU to sleep or perform other low-priority operations. Main, the main function initializes the system, registers the tasks, makes some tasks ready, and then enters the Superloop. How to compile and run *. 1. Save save the code as a .c file, example scheduler.c. 2. Compile use a C compiler, like GCC, to compile the code. For a standard computer GCC scheduler.co scheduler. For an embedded system you will need to use a compiler tool chain specific to your target microcontroller and potentially include specific linker flags. 3. Run for a standard computer */scheduler. For an embedded system you will need to flash the compiled binary to your target microcontroller using a programmer. Important considerations for embedded systems real-time constraints the scheduler must be fast and deterministic. Minimize the time it takes to find and execute the next task. Consider using hardware timers for accurate delays and task scheduling. Interrupt handling when using interrupts, ensure that interrupt service routines, ISRs, are short and efficient. ISRs should typically only set task readiness flags and return, allowing the scheduler to handle the actual task execution in the main loop context. Use appropriate synchronization mechanisms, example disabling interrupts, using atomic operations, to protect shared data between ISRs and tasks. Memory management allocate memory statically or use a simple memory pool to avoid dynamic memory allocation, which can be unpredictable and lead to fragmentation. Consider using a fixed-size task stack for each task to prevent stack overflows. Compiler optimization use compiler optimization flags, example 034 GCC, to improve the performance of the scheduler. However, be careful to verify that the optimized code still functions correctly. Debugging use a debugger to step through the code and observe the behavior of the scheduler. Use debugging techniques like printf statements or a logic analyzer to monitor task execution and timing. Ensure that printf statements are removed or replaced with a more efficient debugging method, example logging to a serial port or using a JTAG debugger, in the final production code. Asterisk critical sections asterisk protect shared resources, variables, hardware peripherals, from concurrent access by multiple tasks. Use techniques like disabling interrupts or using mutexes, if your environment supports them, to create critical sections. Asterisk watchdog timer asterisk implement a watchdog timer to detect and recover from software errors that could cause the system to hang. The watchdog timer should be reset periodically by the main loop. Asterisk task priorities asterisk carefully assign priorities to tasks based on their real-time requirements. Higher priority tasks should be used for time-critical operations, while lower priority tasks can be used for background processing. Avoid priority inversion, where a high priority task is blocked by a low priority task. Optimization techniques asterisk bit manipulation asterisk the scheduler uses bit manipulation for efficient ready queue management. Ensure the compiler optimizes these operations. Asterisk inline functions asterisk consider using inline functions for small, frequently called functions, like set_task_ready, and set_task_unready, to reduce function call overhead. Asterisk caching asterisk if your processor has a cache, ensure that the scheduler's data structures, example tasks, ready queue, are cache-friendly to minimize cache misses. Asterisk assembly optimization asterisk for critical sections of the code, you might consider writing assembly code to achieve maximum performance. Asterisk timer resolution asterisk the accuracy of the timer used for task scheduling will affect the granularity of the real-time performance. Choose a timer with sufficient resolution for your application requirements. Example scenario, motor control system. Let's say you're building a motor control system. You might have tasks like asterisk task 1, priority 0 emergency stop, highest priority. Asterisk task 2, priority 5 PID control loop for motor speed, high priority. Asterisk task 3, priority 20 reading motor encoder data, medium priority. Asterisk task 4, priority 40 displaying motor speed on an LCD screen, low priority. Asterisk task 5, priority 52 handling user input from a button, lowest priority. In this scenario, the emergency stop task needs to be executed immediately if a fault condition is detected. The PID control loop needs to run frequently to maintain accurate motor speed. The other tasks can run at lower priorities. Advantages of this scheduler asterisk. Predictable Superloop architectures are generally predictable, which is important for real-time systems. Low overhead the scheduler implementation is relatively simple and has low overhead compared to more complex real-time operating systems, RTOS. Fine-grained priority 53 priority levels provide a good degree of control over task execution. Disadvantages cooperative tasks must cooperate by not blocking for extended periods. Long-running tasks can delay the execution of other tasks, even higher priority ones. Limited scalability as the number of tasks increases, the scheduler's overhead may become significant. Manual management task scheduling and synchronization are managed manually, which can be error-prone. Alternatives real-time operating system, RTOS for more complex systems, consider using an RTOS. RTOS provides features like preemptive scheduling, inter-task communication, and synchronization primitives, making it easier to manage complex real-time applications. Fixed priority preemptive scheduling if you need preemption, where a higher priority task can interrupt a lower priority task, you can modify the scheduler to be preemptive. This would typically involve using a hardware timer to trigger a context switch to the highest priority ready task. However, preemptive scheduling adds complexity and overhead. This detailed tutorial should provide you with a solid foundation for implementing a 53 priority-based scheduler within a Superloop architecture. Remember to adapt the code to your specific application requirements and carefully consider the optimization techniques and limitations of this approach. Good luck.